Okay, welcome back. This video is going to be on Ampere's law. And we are doing a coaxial cable. So yeah, let's just get right into it. So the currents are uniformly distributed over the cross section of each conductor. So we're assuming that these are kind of like wires. So we're assuming that they're infinitely thin, but also not so thin enough that we can use Ampere's law. And we want to find the magnetic field in between the cables. So between R equals A and R equals B. I did not draw this correctly. Oh my gosh. That is C. Okay. And then we want to find the B field at radius that's greater than C. So let's just get right into it. So our first thing is to write out Ampere's law, which is B dot ds equals mu naught times I enclosed. So let's start with A. The most important part about Ampere's law and finding the B field using Ampere's law is your Amperian loop. So just like how in Gauss's law, we were really sticklers about choosing your correct Gaussian surface, this is the best way for you to find the, this is going to be your way to find the B field correctly. You have to pick the correct Amperian loop. So the first thing that I want to decide on is what direction is this B field going to be in? Because what we ultimately want to do is find our Amperian loop that is going in the same direction as our B field. So I'm looking at this first current carrying wire, and it's inside the, so like the pink one. And the current is coming out of the board. And so our magnetic field is kind of making a loop around it. So it's kind of coming in the phi hat direction if we wanted to talk about our in cylindrical coordinates. So it's kind of moving in the phi hat direction around our z hat direction. So I'm going to, we're going to be using cylindrical coordinates. While we're doing this. So that's rho, phi, and z. So when we're doing this, I'm going to be looking at, we're going to assume that our I is in the z hat direction. And so our phi hat direction is what our B field is going into. So again, it's just the right-hand rule. You put your thumb towards the direction of the current and the B field wraps around it. So now that we know that, we obviously want to pick a Amperian loop that is circular in nature so that it follows the curves of the magnetic field as it moves around. So if I'm going to draw just really quickly, I'm going to redraw this so that you can kind of see what I'm talking about. Okay, so I redrew our coaxial cable. Our I is going this way. And so our B field is going to be going around like this, counterclockwise. So that's going to be our B field between the, when we're just looking at the first I, which is this one. So we want to make an Amperian loop that mimics our B field. So what I'm going to do is say, since we're looking at R is less or greater than A, but less than B, which is right in between where I drew my magnetic field, I'm going to draw a Amperian loop that mimics our B field. So it kind of looks a little bit messy now, but the purple is our Amperian loop, and the B, the pink B, is our magnetic field. So obviously I'm doing something right. They mimic each other, right? So when we're looking at our b.ds, we want to look at their directions. So we have b.ds equals mu not enclosed, I enclosed. So what we're ultimately wanting to do is do exactly like we did with Gauss's law and Gaussian surfaces, and kind of make it so our b is just a constant that we can take out of the integral. And we can do this by, like I said, we have to make sure that our b field and our ds are in the same direction. So, and they're the same type of loop. So in this case, we are going to look at, so again, we can think about this as just a dot product, just these two things. And we can say that it's the magnitude of b, the magnitude of ds, times the cosine of the theta between them, the cosine of the angle between them. But if they are right on top of each other, like I drew in this picture, the cosine of the angle is 0. So this just goes to 1. And now we're left with the magnitude of b times ds, which are both magnitudes. That's what we're left with. So we want to find ds. And so this is going to be kind of similar to what I did in the last video. This ds is just a circle. So we're looking at some value where our radius is constant, and we're going to say that it's some radius r, or in this case, I should say it's our cylindrical coordinates are r, phi, z. I know that's a little bit unconventional, but just go with it. I already defined everything in terms of r. So our r in this case is going to be the from here to our Amperian loop right there. So we've already decided that since our b and our ds are in the same direction, we can now integrate that, and that is equal to mu naught I enclosed. And so in this case, maybe a lot of you kind of already know where I'm going with this, but I'm going to do it just like I did before, in terms of how our ds is found. So our ds looks something like this. Where this is r. And we want to find ds, which is just this is basically just going to be the circumference of the circle. So we already know what the circumference of a circle is. It's 2 pi r. But if you want to redefine, I'm going to do it again. We want to find this little ds right here. And this has a radius of r. Both of these have the same radius. And this has a d theta, some small, tiny angle that we moved from point A to point B in our ds. And we're basically looking for the arc length of this ds. So what we're going to find is that our b ds is actually b times r d theta. B and r are now constants because our radius is going to be the same throughout the entire moving around this Amperian loop that I created. And our b field is also going to be constant. It's no longer a vector. We're just looking in pure coordinates now. So we can take the b and the r out, and now we have to decide our bounds. So the easiest way to do this is say that we're starting at 0 and we're ending at 2 pi because we're creating a full loop around this circle. So I'm going to rewrite this, and it's going to say b r from 0 to 2 pi d theta equals mu naught I enclosed. So now all that I have to do is integrate over d theta. And so that gives me b our theta from 0 to 2 pi equals mu naught I enclosed. And so now we are just left with BR times 2 pi equals mu naught I enclosed. Now, what is our I enclosed? So if we look at our Amperian loop, all that we are showing is this I right here that I highlighted in purple. It's the one that's coming out from the inner cylinder of the coaxial cable. We don't care about this I that's out here because it's not enclosed in our Amperian loop. So our I enclosed is just I. And so now I want to isolate B to solve for the magnetic field. And so what we're left with is mu naught I over 2 pi r. So that is our magnetic field between the two cylinders. And it is in the phi hat direction like we decided earlier. So now let's look at our next problem, which is when the radius is greater than c. So let me redraw our coaxial cable. Okay, so now I redrew our coaxial cable, and we want to make our Amperian loop now greater than c. So I'm going to do the same thing, and we want our Amperian loop to be right here. I'll even make it purple so that you can see. Right there. So we're going to do the same thing. B dot ds equals mu naught I enclosed. So you can already see that the Amperian loop is still going to simplify to our B R2 pi, like I defined above. But let's look at our I enclosed real quick. So we have two I's that are enclosed now because our second I is now in our Amperian loop that I created. But they have the same magnitude. One's going in the positive z direction and the other one is going in the negative z direction. So in this case, our I enclosed is equal to I, which is the one that's flowing in the positive direction, minus I, which is flowing in the negative z direction. So our I enclosed is equal to 0. So if our I enclosed is equal to 0, what must our magnetic field be equal to? Right. So if we have no current enclosed in our Amperian loop, the magnetic field is equal to 0. So I hope that this was helpful to kind of going over a Ampere's law problem. If you have any questions, feel free to reach out to me. And don't forget that exam 3 is coming up next week. Keep studying hard. I believe in every single one of you. And I know that you'll make it through this semester. I hope you guys have a great rest of your day. Have a good weekend, and I'll see you later. Bye.